Let's take an example. What is the difference between what we are doing and what you are expecting in the assignment or in the examinations? So if we have the circuit here and you are given a source, and this source say is 100 volt 60 hertz, and you need to sketch V out, I out, V diode, and Vn. So what will be the difference? The difference here is that you are given the values here. So this 100 volt is RMS. So the maximum of the source value will be 100 root 2. So when we are sketching here, we are looking for the values that we will write down. So here we are sketching the input voltage. So this value will be 100 root 2, and this value will be negative 100 root 2, and this is V of t. And this will be pi, and this will be 2 pi. You can write this in seconds as 1 over 60 seconds, because you are given the frequency as 60 hertz, or you can just leave it as angles pi and 2 pi. And when we are sketching V out, it will be the sine wave, then it is 0, and this value here is the same 100 root 2. So this is what we are looking for, these values. And when we are sketching I out, say this R is 10 ohm, and when we are sketching I out, so these sketches are not to scale, so this will be 10 root 2, and this is 2 pi, 2 pi, pi. And when we are sketching V diode, it will be 0 here, and here it will be negative 100 root 2, because it will be the same as Vn during the off period of the diode. And this value here is very important, because this value is the peak inverse voltage, the PIV of the diode is 100 root 2. And PIV, you are saying it is the peak inverse voltage. You are saying it is inverse. So please don't put negative here, okay? So don't put negative. So it is already, you are saying it is inverse. Inverse means it is negative. So the peak inverse voltage is 100 root 2. So if the values are given to you, just you will put the values on the graph, and this will be the difference for what we are studying in lectures, because in lectures we will study it in symbols. So I will use Vmax over R, but in the assignment and in the exam, it will be values, okay? So to calculate V average, it will be Vmax divided by 2 equal 100 root 2 divided by 2. So it's 50 root 2 volt. And as you can see, that the average voltage is a single value, and that's why we call this as uncontrolled rectifier. So when I ask you to calculate the average for this problem, you have to do the proof first until you reach what is the expression for V average, and then you find the value. So you need to know how to do integration, okay? To find I out average, it is V out average divided by R equal to 50 root 2 over 10 equal to 5 root 2 ampere. Sorry, this value is not correct. I used the RMS instead of the average. So these are the RMS values. So this is V RMS, this is I RMS. So V out average equals the V max over pi equal 100 root 2 over pi volt. I out average equal V out average divided by R equal 10 root 2 over pi ampere. To find P out average, we will use V out RMS squared over R, or I out RMS squared R. So this is equal 50 root 2 all squared divided by 10. Equal to 500 watt. So these are the calculations. So usually the power electronics part will be sketching. So you start by sketch, then followed by calculations. Okay, so you have to prove the formula. So you need to write down that V out, for example, average equal to 1 over 2 pi integration from 0 to pi V max sine theta d theta until you reach that V average is V max over pi. Then you can substitute. You cannot just substitute for the value. The last point here. Okay, I will give you low rating notability. Okay, I don't know what happened here. It's not moving up or down. So just a quick note here. What if we have this AC source, then we have the diode. So this is a single phase half wave rectifier, but in this case we are connecting it to the armature of DC machine, for example. Okay, so this is a permanent magnet DC machine. Okay, so how we can study this? If we need to study this from power electronic perspective, we will sketch the graphs or sketch the waveforms and we can do the calculations. But if we need to analyze the machine, if we need to study the machine, so for this machine here, we can sketch a battery and we can sketch our machine. The value of this battery here is V average, which is V max over pi. And that's it. You do your you do business as usual. Okay, so you say that V armature equal to EA plus RAIA, but this V armature is V max over pi. That's it. So this is from the machine perspective. So if we need to study the machine, we will do the following. Just we will find the expression for the average voltage and we will use it. But if we need to study the power electronics, we will represent the machine as R, L, and E. R armature, E armature, or the back EMF, and here we will have the inductance. And someone will say, okay, when we studied DC machine, we didn't see inductance. Okay, this is for steady state DC. Now your supply is not steady state DC. Your supply here is changing. So this is the source you have. So the source here is not a steady state DC. This is not a steady state DC. It's not constant. So the inductance will have an effect. So to study this circuit from the power electronics perspective, we will study the circuit with a load, and this load is R, L, and E. So for power electronics, which is this chapter here, so this is chapter 5, our goal is to see how the power electronics will react with this type of load, R, L, E load. So this will be our ultimate goal. And this will we will do this in steps. So we'll start by R load, then RE, then RLE, then we will reach a general state where we have the RLE. Okay, so in this part of the chapter we just studied the rectifier with only R load. So we started here just with R load. Next lecture we will add the battery, and then we will add the inductance, and we will see what will be the effect. And to study the controlled machine here, this will be our chapter 6, is seeing how the machine will react when we have the power electronics. Okay, so this is how we will model the machine into the power electronics. So this is how we will model the machine into the power electronics, and this is how we will model the power electronics into the machine. Okay, so I will stop the lecture here and see you next lecture. Continue with power electronics. So for power electronics, we will start by a quick summary for what we did last lecture. Then we will continue. So we covered so far the introduction and the first semiconductor switch, the diode, and we can see, or we discussed, that the diode is uncontrolled. So the diode will turn on when V diode is positive, and the diode will turn off when I diode goes to 0. So you have no control over the diode. That's why the diode is used for an application called uncontrolled rectifier. So diodes will convert AC to DC, but the DC you have is uncontrolled. So for uncontrolled rectifier, we studied single phase half wave rectifier, single phase half wave rectifier, or we write it as single phase half wave rectifier. And for single phase half wave rectifier, we studied an R load. Today we will study an RE load, and we will see the effect of having an inductance. Then we will move to single phase full wave rectifiers, and by covering the single phase full wave rectifier, we will move to our next switch, which is thyristors, and thyristors are controlled diodes. So we will go through the controlled rectifier. Then we will have a mix from thyristors and diodes, which will be a semi-controlled rectifier. So I have this example from the posted textbook on Learn. At the end of the chapter for power electronics, you will find 3 examples. This is one of the examples. So this example is for half-wave uncontrolled rectifier circuit. The supply is 110. So this 110 is RMS for sure. So any given voltage is RMS. The average voltage, we need to calculate the average voltage and output current. So given here that the frequency is 60 Hertz, which means that T, or the cycle, is 1/60 seconds. So this is our cycle time, which is equivalent to 2 pi radian. The load here is a resistive load, so we are supplying an R load. So we are in this application here, a single phase half wave rectifier supplying an R load. And the load resistance here is given as 25 ohms. And we need to calculate the average value, and this average value for the output voltage and current. And then we need to find the RMS value. And the RMS value we need it for the output voltage and current. And then we need to find the power average. So we need to find the power average. So we need to find the output voltage and current, RMS, the output voltage and current average. We need to find the average power delivered to the load. And the average power delivered to the load if the supply has a 60 ohm resistance. And this is one of the good tricks that can be added to this kind of questions, okay? Which is a circuit trick, okay? You should be able to solve it. Okay, so here we have the circuits that we studied last time, but usually this kind of circuits, which are the rectifier circuits, usually they are supplied from a transformer. For example, if you need to supply your laptop, okay, and your laptop need say 5 volt, and the source you have at your home is 110 volt AC. So what we will do, we will put a transformer. Say this transformer is 110 to 5 AC. So the peak value of the AC here, the maximum value will be 5 root 2. Then we can put a rectifier circuit, and this is how we sketch it. So you can get 5 volt DC. So no one will rectify the AC directly. First you change the level of the voltage, and then you rectify it. Okay, that's why here I added this transformer here. This is the first stage in most of the rectifier, and we will assume that this transformer is ideal transformer, or doesn't matter if it is not ideal transformer, just you'll use the approximate circuit. Now we did the sketch last time, so we sketched V source. So the value here is V maximum, which will be 110 square root 2, because the RMS is 110. This is pi, this is 2 pi, and 2 pi is 1 over 60 seconds. Okay, these are the values we are looking for. And the negative value here is negative 110 square root 2. The maximum value for V output will be 110 divided by root 2. For I out, it will be 110 root 2 divided by R, which is 25 ohms. V diode, the value here is negative 110 square root 2. And we mentioned that this value is a peak inverse value, or peak inverse voltage, 110 root 2 volt. So we did the sketch last time. This is a numerical example. Now, if we need to calculate V average, you have to write the average equation. So the average is, the duration is 2 pi, and the integration from 0 to pi only, because the wave is available from 0 to pi. And the wave is a sine wave, so it's V max sine theta d theta. So this is a sine. So this is a sine wave. So this wave here is a sine wave, which is the main supply wave. So the equation here will be V max over pi, which is 110 root 2 divided by pi volt. I out average is V out average divided by R, equal 110 root 2 divided by pi multiplied by 25 ampere. To find V out RMS, it is square root for 1 over 2 pi integration from 0 to pi for V max sine theta squared d theta, which we did the proof to be V max over 2, or 110 root 2 over 2 volt. So in the exam you have to do the integration, okay? You cannot just write down the final answer. So then we can get I out RMS as V out RMS divided by R, equal 110 root 2 divided by 2 multiplied by 25 ampere. So we got V out average, V out RMS, I out average, and I out RMS. Now we need to find the average value of the power. So as we mentioned last time, that P out average is V out RMS squared divided by R, equal to 110 root 2 divided by 2. This is V RMS squared divided by 25 watt. So we can find P out average. And then what will be the average value of the power delivered to the load if the source has a resistance of 60 ohm. So what is the meaning of this? So it's like you have a resistance here of the source, then you have a resistance of the load. This is the load, and this is our source, which means the voltage across the load is not the voltage output. This is V out. So here your V out will be between our load and our source. So simply here, you can do a voltage divider, okay, by using the resistance ratio, which is what we have here, okay. Or you can find the power using the power equation and then do the analysis. So what we will do here, we used here voltage divider rule to find V out, and then we can find P out average. So here we will use voltage divider rule. So V over the resistance will be V out of T multiplied by R load divided by R source plus R load, and this is voltage divider rule. So the power P as a function of time will be V of the resistance multiplied by I out. Why? Because I out is the same current in both resistances, because both resistances are connected in series. So V of the resistance is V out multiplied by R load divided by R load plus R source multiplied by I out of T dt, and this is P of T, sorry. So this is the power as function of time. Sorry, just I will remove this. To get P average, so we will take 1 divided by the duration pi, or 2 pi. Then we will integrate this equation from 0 to pi. V out is V max sine theta. I out is V max sine theta divided by R. And this is multiplied by this voltage division rule, okay. Or someone will say PR of T will be V out of T squared divided by R load, and V out of T is R load VR. VR of T is R load divided by R load plus R source multiplied by V out of T, this is a voltage divider, squared divided by R load. So P resistance of T equals to R load divided by R load plus R source, and here all squared divided by R load multiplied by V out of T squared. So P resistance of T equal to R load divided by R load plus R source all squared multiplied by V out of T squared over R load. This term is the original power, okay? So this term is the original term to calculate the power if we don't have our source. So if we don't have our source here, the power P out is V out square over R. Now this power is scaled by this factor. So what you can do, you can say that your P average will be the value we calculated here for the power, this value here, the value we calculated for the power, but we will multiply this by this scale factor here. So someone will follow this path instead of doing the integration of a sine square here. Okay, so this is one approach, or this is the second approach, which I would recommend the second approach. Okay, so these are a little tricks that can be added to a typical power electronics question. So here just we mentioned that there is a resistance added for the source, and in this case the voltage across the resistance is not V out, so you have to use a voltage divider. The numerical solution here is available, and it is available on the posted chapter. Okay, so this is a quick example over what we did last time. Please note that these little tricks can be part of any circuit. Okay, so we can add the source resistance to any of our following circuits. So each circuit that we are studying will give you part of the information, and this information has to be integrated together. So in the exam we can put these things together into one big example. Okay.